Okay, next presentation by Alshammari. It begins now.
Yes, thank you. Thank you, ladies and gentlemen. Pleased to meet you in this congress. My name is Yousef Alshammari, and I'm a PhD student at Imperial College London. I'm finishing my PhD in hydrothermal gasification of hydrocarbons. That has been my PhD over the past 4 years. I'm working under Dr. Klaus Helgaard and with academic mentoring of Professor Jeff Maitland. My project here is partly technical compared with the previous presentation on the financing and smart metering. So we are looking into the production of hydrogen from oil resources as a clean energy vector. If we look into the current energy scenario, we find that most of the energy sources currently is the oil, the renewables in the form of solar, wind, hydroelectric. We have the nuclear energy vector. We have also the natural gas. And this figure shows you the fractions of energy, the demand, or how much supply we get from each of these energy resources, going into the electricity grid or the consumption of energy in the form of heat. Of course, this energy would go into the transport, into the heat and the residential, as well as the industry, leading to high emissions of carbon in the form of CO2. So to mitigate that, we suppose that the hydrogen economy is one way where we have a cleaner and more sustainable energy infrastructure. So we think that hydrogen economy, we can get it from hydrocarbon, coal, in addition to renewable, nuclear, as well as biomass. Hydrogen goes into integrated gasification with carbon capture. That's some sort of power generation with capturing carbon dioxide. It could go to electrolysis. It could go to. We can also get hydrogen by a thermochemical cycle, which gets energy from nuclear plants. We can get hydrogen as well from gasification. Hydrogen, and once it gets produced, it could go to the electricity grid to supply our electricity. It could also go to the hydrogen network where we can use it as a fuel. So hydrogen could give us heat, it could give us electricity, and it can be used as a fuel. And in this way, we can capture all the CO2, we can mitigate the CO2 emission, and we can also store the captured CO2 underground and permanently, or perhaps convert the CO2 into some high value chemicals. So that's the final message. Hydrogen is seen as a solution to the world's environmental energy crisis, but to succeed in this journey, we need to find how we can recover the hydrogen atom, how to produce it, how to store it, to transport it, and deliver the hydrogen to the end consumer. So my project now is how to get hydrogen from underground gasification. So we designed a process where we get the hydrogen by a hydrothermal conversion of heavy oil under high pressure, high temperature conditions. So the assumptions assumed here is that we have a temperature supplied by the geothermal as well as the injection of oxygen. We can also get the temperature by injection of steam. We can place some catalyst in the form of water-soluble catalyst or dispersible nanoparticles. And in this way, once the hydrogen gets produced, it can go to an above-surface processing plant to do a water-gas shift reaction to maximize hydrogen yield. We can get ammonia, which is another energy vector, or can also be a good chemical for fertilizers. We can get an air separation process above surface, where we inject the oxygen and using the stripped nitrogen can be supplied to an ammonia vapor process. So the hydrothermal gasification now, why do we do it hydrothermally? Hydrothermally is basically achieved under high pressure, high temperature conditions. And from science, at the hydrothermal conditions, you have the increase in dielectric constant of water, as well as the ionic properties of supercritical water. It makes it homogeneous with oil, with heavy oil under these conditions. And under these conditions, you have the dielectric constant of water equivalent to many organic solvents. And in this way, you have a homogeneous reaction going at a higher reaction rate and even at a better conversion. And these reactions are already established in the industry, how they get hydrogen from conventionally. So we can apply them underground with even better properties using hydrothermal water. So this table here shows you the differences between each of the conventional production of processes and the hydrothermal process, which is proposed during underground gasification. So during my modeling, we did thermodynamics, we did also CFD, and in the thermodynamics, we studied the reactions using direct minimization of Gibbs free energy and the Ring-Robinson equation of a state. And in the CFD, using some experimental data, we designed some tubular flow system using energy and energy balance and mass balance equations embedded already in software called COMSOL. So using these two modeling techniques with some experimentation, we could extract some good data which could enable us to doing this process at a large scale. And this graph here shows you the experimental rig which we have designed in Imperial College labs. And using this rig, we have been able to get some good experimental data, which could be used for some for modeling. And this modeling then could enable us to design some real processes for such hydrothermal conversion. So we have already done some good thermodynamic analysis, and we have investigated the yield of hydrogen and carbon monoxide, which when it gets with hydrogen becomes syngas. And syngas is a good energy vector for methanol conversion, for example. And we studied the optimal conditions by which we enhance the syngas ratio. That's the rate of hydrogen and carbon monoxide and the different water to carbon ratio. And we have managed to publish our results at the International Journal of Hydrogen Energy. And then we did some experimental work, and we studied the conversion of oil and the different residence time, and using the conversion data, we extracted the kinetic data from the conversion data, and we have been able to produce these two equations, which can be now fit into a model to enable us design a real georeactor. So then we did the process, studied the effect of oxygen in order to minimize temperature. And using oxygen, we have been able not only to produce hydrogen, but also to produce some oxygenated product contained in the oil phase. And you can see from the GCMS chromatograms and this figure that these chemicals could also add a value to the oil that gets produced from underground. And also we have achieved a high gasification efficiency under much lower temperature with a high hydrogen selectivity by the use of oxygen. And then using these experimental data, we developed a new CFD model which simulates the conversion of heavy oil under high pressure, high temperature conditions. We studied the reaction rate here. We also studied the conversion. We looked into the velocity profile under laminar flow condition. And one good thing is that we extrapolated a better kinetic data taking into account the laminar flow effects, which considers the mass transport limitations, which are not considered during lab analysis. So then we developed another subsurface model. We look into the energy efficiency of the whole process. So we look into the energy efficiency of injection of fluids and how much energy you can get out from the heat of the gas as well as the momentum pressure of the gas. And these two equations shows you the energy considered to compare to the energy recovered, as well as the gasification efficiency, which is how much carbon you get in the form of gas compared with the carbon contained in the oil. And using this model, we got these correlations, and we found under what conditions we can maximize the energy efficiency of the process, which enable us not only to get energy in the form of heat and pressure, but also to get hydrogen as well. And that shows you that the process can be energy efficient, and this will enable us to do some further techno-economic analysis, giving the energy efficiency analysis of our process. So my conclusion out of this work is that the new models have been developed, to enable us for some future work into scaling up this process. We determined some optimum conditions from the thermodynamics. We understood the key experimental effects, and we determined some new kinetic data. And the results of our analysis showed that the carbon coke formation, which is usually produced under conventional production, was minimized under hydrothermal processes, and due to the high flow rates of water. And this result shows you as I just mentioned, the potential of recovering clean energy from underground gasification. And for future work, I suggest that we study the potential for capturing carbon and re-injecting it into a depleted oil reservoir, and looking into how would this balance with the whole energy analysis again. And we can also investigate the effect of feed composition, including sulfur, nitrogen, which are already contained in crude oil, and this will enable us to study in a better way the scaling up potential for this process. This is the lab which I have built and constructed, and thank you very much for listening. Any questions?
Thank you very much for interesting. In order to give you a fair amount of time to each presentation, we have to keep the